First of all, I'd like to thank the organizers for organizing this and also for giving me the opportunity to talk about time series forecasting. So that's what we're going to talk about. First, it will be kind of a tutorial / info talk. So the first part is just a few slides, and then I will go through a notebook, which is online, so you can follow that along right now, or in your own time later. So let me first quickly pull up the link. So you can, if you want to, you can open the notebook. You probably want to change the runtime to GPU, so it will run a bit faster because we're going to use some PyTorch under the hood. So I leave that up open a few minutes, but in the meantime, let me ask you some questions. So of everyone here, so who has worked on time series, either professionally or as a hobby? All right, a few people, that's good. Who has taken classes in time series? Fewer people. Who went through all the ARIMA stuff? And who thought it was exciting? No one. Oh, no, two people. All right, yeah, so this is actually what inspired me a bit to give this presentation, because time series forecasting, I mean, it's used all over the place, but somehow people either think it's boring or they associate it with lots of ARIMA stuff, and I think neither of the two is necessarily the case. So I was going back and forth a bit what I wanted to touch upon. So I'm going to not explain how models work in detail. I'm going to give you an overview of different techniques, different types of problems, different ways of solving it. And then just so that, yeah, if you want to try it out yourself, you know what kind of tool set is actually available. So here we go. Another technical hiccup. So, all right. So what is a time series? Maybe it's obvious, but it's basically values you observe sequentially and typically at a regular interval. And that can be pretty much anything. So we'll have quite a few examples. So this is like, can be the hourly temperature, can be share prices, daily share prices, or sales, inflation, whatever. Pretty much everything. If you have a graph where the horizontal axis is time, and then you have some numerical value on the vertical axis, you can almost call it a time series. And all right, so that's what it is. So what do we want to do with it? So this is well, the prototypical time series. We'll see this graph over and over and over. But say you know the first bit, the past, and all this is what you know. You want to predict the future. So I've plotted a few possible outcomes. So we have these three different scenarios. They all seem reasonable, but we obviously want to pick the best. We want to have a mechanism to produce these and also to, yeah, give some confidence which one we think is best without having seen the future yet. And what I find interesting about time series forecasting, if I go to my 9-year-old nephew, and if I show him this graph and ask him what goes next, he would probably plot one of these graphs. He doesn't know anything about machine learning, obviously, but he has some intuition of like what comes next. And then if I would ask him like, so why would you draw a line like that? Then he would say, well, I asked him this, so he's not here for obvious reason. But he said, well, it goes a bit up. All right, so let's call that a trend. And then there's some pattern there. All right, so there's some seasonality. So basically, there's a reoccurring thing. So although the system may change over time a bit, there is some underlying structure. And in time series forecasting, you try to leverage that structure to make predictions about the future. Okay, so how is this different from traditional machine learning problems? So if you first look at the machine learning problem, so you have some, well, y, which is your target variable, which is what you want to predict. And then you have some features, x, and you try to find a function so that you can describe your data with a minimal error. This is typically how you would formulate a supervised machine learning problem. In time series forecasting, two things are different. A, you no longer have the X, but it's just the previous data itself. And so I labeled them with all the time indices. And then the other thing, which is, I think, interesting, there is a concept of a horizon. So you can make a prediction for, like, if you go back to this example, so this is monthly data, and you can make a prediction for the next month. But you can also say, well, I want a prediction for the next 12 months. And they're both use cases for these things. And especially if you think on longer horizons, it makes it a bit more interesting compared to traditional machine learning. Then we have the third category, which is basically the mixed problem. So you use previous values, but you also have some extra features to explain your data. And so I will not talk about the first one, but I will talk about the second and the third. All right, so let's get started. So if you do traditional machine learning, I mean, typically I first go to scikit-learn, and that has most of the stuff. Time series is not there yet, in my opinion. I have here like 4 different libraries for time series. They all have slightly different interpretations, pros and cons, but there is not one that really stands out in my mind. I think, well, in a few years' time, one will evolve as the dominant one. For this tutorial, we're going to go with the top left with Nixla. And the reason I chose that one, I'm not affiliated with them, but they have the most up-to-date models. So that's why I chose them for this tutorial. Alrighty, so then this is the slide. So I'm going to go to the actual collab. Another. Seems like. Here we go. All right, so I have some introductory stuff at the beginning. So the one thing, if you run this notebook on Colab, it takes a lot of time to actually install these packages, but that's the slowest bit of the whole notebook. So if you're trying to follow along, just evaluate the whole thing. I already evaluated it at the beginning, so we don't have to wait for things to finish. But it will be, if you run this in your own time, it will be pretty quick actually to run the whole notebook, a few minutes.
Where's the file? Like the file? It's not in there.
Yeah, but you can use the Colab, right? But yeah, I can add the requirements to the GitHub. All right, so we'll have an overview of various models. I will touch upon some of them, but please remind me at the end that I will go back to this, so to give a more formal overview. And we'll have 3 examples, which we'll tackle in a slightly different way. And if there are any questions, then feel free to ask and interrupt. So example 1, we've already seen this graph. So that's the airline passengers. And this is for anyone who ever worked with time series. I'm pretty sure you have seen this graph before, because this is the Hello World example. I don't know the reason why, but everyone chooses this example to test their models on. I mean, I guess it looks really nice, right? It has a really nice trend and seasonality. And I probably have to disappoint you that if you're going to work with time series, typically it will not look as nice as this one. So you have to work a little bit harder. But, well, as a first example, I thought, why not? So coming back to my nephew, who said, like, yeah, I can predict this. And he basically, well, not in his words, but was thinking about trend and seasonality. So let's actually try to do this mathematically. What we want to do is, if I have my, can you see what I highlight? Yeah. So if my y of t, which I want to, let's first say explain. We were not forecasting yet. I can say, like, okay, it's composed of 3 components, some trend component, a seasonality component, and some residual, the piece that we don't know. And we can either add these terms or multiply. Those are the two typical modes. All right. I mean, if you think about it, there are many ways how you can implement this, but I'm just going to run the code, and we'll see what happens. From the packages, right, which I installed, so the Nixla packages, so we have the stats forecast that focus on classical methods, and then later on we will use the neural forecast for neural network models. So what you need to do is you need to instantiate a forecaster object, and you need to specify it what models you want to train it on. So for now we have only one model, so that's the MSTL. So it will decompose in seasonality and trend. I have to specify what the seasonality is. So that's typically, if you're working with monthly data, then that will be 12, obviously. So it's basically the frequency of the data tells you what you have to put there. And then we put in the data. So let's see. So I loaded the data here, and I for this example, I have a train in the test set. And the test set is just the last 12 months. So I run the fit on it, and actually I used just a built-in function to decompose this. So for this particular model, you get a nice decomposition. So on the top left, you get the original data, which we started with. And then the second one, that's the fitted trend. So you see it's not a straight line, but it's going up. So basically they do some sort of kind of local linear regression to figure out what that trend is. And then they overlay it with a seasonal component. And if you look at what that seasonal component is, the amplitude is growing, but the pattern is actually pretty much the same in this case. So that's something specific to this model. And then we have the remainder, the residual. And if you look in the middle, the residual is pretty close to zero, so it's really good. But you already can see that at the end, you have some bigger residuals. And if you are going to forecast, then obviously you're going to be on the right-hand side here. So this is not necessarily a good sign that we're in a good business with this particular model. But let's forecast it anyway. So we go back to the same object, and we say predict, and we have to specify how many months we want to predict. So that's 12 in this case. So I plotted the results. So the orange one is our prediction. I mean, if you see this like, meh, right? Yeah, it's going up a little bit, not as much as you expected. The seasonality is there. So maybe not the best forecast we can do. But the reason I started off with this model is it has a clear trend and seasonality component. All the other time series models don't necessarily have such a nice decomposition. They still leverage trend and seasonality and other structures under the hood, but it's less easy to plot these things. So this was the first attempt of forecasting. So let's go to some other classical methods. So two classical methods that stand out, the ARIMA, which I already mentioned, and then you have exponential smoothing, which in my mind should be on par with the ARIMA model, but somehow people mainly focus on the ARIMA. I'm not going to go into the details of the ARIMA, but for the people who raised their hand when they followed that in class, you have to specify some hyperparameters. Not going to go into these differences, but that can be annoying to specify these hyperparameters, and maybe at school you actually taught the procedure how to do that, but if you say have 1,000 time series, you're not really going to do that. You want to do that automatically. Oh, here we go. What I actually built is something called outer ARIMA, which does the hyperparameter, choosing the optimal hyperparameters under the hood. And this implementation by Nixla is actually really fast. It just tries out various models, and then it picks the best one. So let's see. So we run these things. Let me show the output again. So now we have these two outputs, so the ARIMA and the ETS, which is the exponential smoothing. And these predictions look actually pretty decent. You see that the first theorema is really on top of it, and then at the last few months doesn't do as well. And then for the exponential smoothing has the exact same, the opposite impact. It doesn't do so good at the peak, but actually the last few months it happens to exactly predict those. Okay, so for now we have been judging the predictions by just looking at the graph. That's obviously not very systematic. So how do you predict this in real time? So there are two, well, there are actually in time series forecasting loads of different ways of how to evaluate forecasts, debates, different camps and whatnot. We're not going to go into that. I will just show you two common metrics. So one is the mean squared error, which is basically what you most of the time use in traditional machine learning anyways. And then we have another one, which is basically you take the percentage difference, which like if you try to predict the airline passengers, you just say, all right, I predicted like 1,000 and happened to be like 1,100. Okay, so then you're off by 10%. And that's at scale independent, makes it nice if you have to, well, relay this back to stakeholders, because that's not something that the mean square error gives you. That is nice for comparing different models, but not necessarily a good measure of like how accurate the forecast is on its own. Okay, so let's see. So I ran these numbers here. So we have, sorry for the poor formatting, but yeah, the lower the better. So the ARIMA is the winner with 4.2%, and then closely followed by the exponential smoothing, 4.4, and then the MSTL is around 5%, so not even that bad. In my experience, a lot of cases, if your time series is not that complicated, or these methods can actually already be sufficient for your problem. So my recommendation is to actually always first try out some of these few models. They're super fast to fit. Yeah, you can easily just compare a few and see which one works best. Okay, but I promise you that I would also talk about something new stuff. So I think until like a few years ago, so every so often they have these time series forecasting competitions. So you have like the M3 and 4 and 5. Maybe some people have heard of it. But that is basically the, well, if you win that, that's the, I don't know what the equivalent it is, but a Nobel Prize equivalent for time series forecasting. And the nice thing about these forecasts is you have a lot of theory of like what should be good methods and whatnot. So I can try to convince you based on this graph, like, oh, try really this method. But there, these methods are tested over thousands of time series. And until 4 years ago, the methods I just explained, the ARIMA and exponential smoothing, they would typically win these forecasts. Maybe not standalone, maybe clever combinations, but that was the case. And although neural network techniques were around, they would just not beat those, or they would be very slow to fit. And in the last few years, that has been changing, actually. So that's quite interesting, opens up a lot of new possibilities. So I want to explore a few of those. So here we go. So I picked 3 different neural network models. So we have the LSTM. I guess a lot of people have heard of that, very generic neural network model for sequences. And then I have 2 newer ones. And these are really released like only 2 years ago, or maybe 1 year ago. So you have the patch TST that's based on the transformer architecture. And then you have the LMP, that is basically a standard neural network architecture, but tailored for for time series. So when I went back to say, let's decompose this time series in trend and seasonality, that's basically what they built under the hood with that architecture. Okay, so these methods, I have to import a different class. So this is now the neural forecast class. I specify the models. I chose some basic parameters here. I try to make it a bit fair between them, but obviously this can be tuned. So I chose the max steps for 200 for each of them. That's basically the amount of iterations we're going to train the models. So again, I feed it the same, the train set, and then we're going to do the predictions. So I think if you run this on Colab with a GPU, this takes under a minute, it should. So let's go look at the predictions. And well, we'll see that, so we have again the blue line, which was the actual values. And then we see that the patch TST and the N hits, they follow really closely, and the LSTM is completely off. And I somehow left it on purpose. And I mean, maybe someone wants to guess why that happened. Any guesses? Yeah, well, too little, not necessarily in this case. So this is a tricky thing. So if you go back to the slide, you see the values go, sorry? Yeah, but there is actually a simpler explanation here. We see that the trend goes up and up and up. And it just has never seen values that big. Yeah, so I mean, obviously, there are many ways to fix this. So I mean, so you can definitely pre-process your data by taking, say, a log transform, taking the differences and whatnot. If you do that, then your LSTM will be way better. So it's not like a reason to dismiss the LSTM, but if you, I guess, if you're not a seasoned time series forecaster, and then if you just try these models, then yeah, this is a typical thing you can run into actually. So this is something to be aware of. It's actually surprising that these other models just run out of the box and have really good predictions without any tweaking from my side. But also disclaimer, we're still looking at the same time series over and over, right? So don't draw any general conclusions from this one particular forecast. But let's look at the results. So I have the same MAPE here. So the LSTM is 12%, so that's by far the worst we have seen. So then we have the patch TST, that's 3.9%, and the other one rounds to 4. So these newer models for this particular model happen to give more accurate predictions, but they're actually a bit slower to train. So this may not necessarily your go-to model. It depends on like how fast you want it to train or how accurate you want it. But this is in a nutshell. If you use the Nixla, you can quickly try many models, see what works best. I don't think there is really sophisticated theory that tells you which model is going to work for your particular time series. All these time series have different characteristics, and all these models, they work slightly differently. So this is just, I guess you have to test it out. So this almost finishes the first example, but I want to add one extra thing, which I think is important when you do the time series forecasting for a long horizon. Because, I mean, we forecasted for like 12 months. I could have easily said like at 1200 months and we got a really long prediction, but obviously no one is going to buy that if we trained it on only like 10 years of data, and I'm going to make a forecast for like, I don't know, 100 years of data. That's not really credible, obviously. But even with 12 months, you can argue like, can you really forecast 12 months ahead? So you want to actually have something like a probabilistic forecast. And basically what you want to do is you want to have a prediction interval. So I run the same models. I'm not going to go into the details, but I specified some prediction intervals. So I have from 5% to 95%, which basically means that in that band, you expect 90% of the time to follow your observation within that band. And I can make a slightly narrower band between 25 and 75. And that gives you an idea of like your confidence about that. And as you can see, the blue one roughly goes through it. Once in a while, it's outside. But what you can see is on the left, we start quite narrow, right? So this is the beginning of the year, so January, and then we end up in December, 12 months later. And the band is almost twice as wide, which reflects that we're forecasting far ahead. They're actually, I'm just going to name drop here the conformal predictions. That is something very new. I mean, has been around for like 2 years that it caught on in the mainstream time series forecasting. It's a way to guarantee that you actually have these unbiased prediction intervals. So something to keep in mind for the more seasoned forecasters. All right, so this concludes example number 1. I will rush through the other 2. As I said, you can have the traditional time series model, and you have also something like a mixed model where you use some extra data. So I picked an example I'm very familiar with, energy demand forecasting. So if you look at the demand historically, that looks something like this, and we want to predict that. We can use classical time series. I mean, you can clearly see there's some seasonality in there, so we can try to fit that. But with energy demand forecasting, you actually, if you want to do a really good job, you need to know the weather. Because most of the energy demand is either heating or cooling. People either turn on their AC or they cool. That is where the bulk of the energy demand comes from. So if you know the temperature, you can typically, well, forecast the temperature. You can make a good estimate of what the demand is going to be. So we'll work on a model that incorporates that. But I want to introduce one second topic, is called backtesting, aka cross-validation. So the previous example, we just had fixed our train set, and then we just made a prediction for the next 12 months. I mean, that is sometimes the case, but often you want to have a prediction on a rolling basis. Say every month you want to just predict the next month, and then you refit your model with the latest data, and you want to see how well that model does. So in traditional machine learning, that's just the n-fold cross-validation. With time series, you just have to be careful that you always, you never train on future data to evaluate past predictions. So in this diagram, we just have the blue, that's always what you train. We always evaluate on future data. So you can roll it, so you start, this is the first evaluation, and then you add, you shift everything by 1, and so on. So that's what I did. So I started first, for this example, I said, let's first assume we don't have the temperature. So I specified, in this case, I chose the neural network model and hits. I had to specify a few extra tweaks so that we don't overfit. And then now instead of fit, I run this cross-validation, and that gives me a complete backtest. So if you look here, doesn't look that impressive, but hey, this is often what real data looks like. So this is the blue one, and you see the, like, I forgot, like, this is like, I guess, yeah, a 2-week forecast of energy demand. And it's not too bad, even without knowing the temperature. But let's see if we can actually add that. So before we do that, so I have a graph of historical demand versus temperature. So even though I said it's clearly related to each other, it's not really a nice linear relationship, obviously. So this is the min temperature of the day. I also have the max temperature, but you see like a strong response here for cold temperatures. And then somewhat that response is also slightly there for higher temperatures. But it's a nonlinear relation we somehow want to incorporate into the model. So various ways to do that, but that's why I picked this neural network model, which has no problem fitting that. Yes?
The question is, if you were the same kind of model, but let's say the secondary variable wasn't, let's say if it was a different kind of Celsius or Fahrenheit, let's say it was the undo second variable help.
Yeah, but it depends on the model how much helpful that would be. But yeah, I mean, it's definitely, say, for temperature, you can actually, if you try to transform that into something linear, more models are going to know how to incorporate that. So I did that not, I didn't do that here, so I really focused on the time series piece. So I fit these two things, And then let's see what the results are. So we have now the orange one, which is without the extra temperature feature, and then the green one with. And it's maybe hard to see from the graph, but the green one, as expected, follows the data slightly better. And then if we go back to our MAPES, we see initially we had something like 5.1%, and then we reduced it to 3.9. So there's an improvement. I know you can do better than this, and the way to do even better is not only incorporate temperature, but lots of other features that will tell you that. But that's my work, so I'm not going to go into details on that. So that's example number 2. And then lastly, number 3. I think this is an interesting one. So in machine learning, we have the concept of transfer learning. So you train your model on one set of data, and then you apply to make predictions for, say, a new set of data. Again, I used something from energy demand, but doesn't have to be. So this is like you have in the Midwest somewhere. You have various zones, and we all have historic demand data for that. So this is like we have 8 zones here, and as you can see, there's a lot of similarity there. You see very similar patterns, and that is obviously expected because it's the same thing, just in a different neighborhood. It's only that the magnitude can be a bit different. But for this experiment, what I did is I trained a model on the first 7 time series, but I exclude number 8, also called FE in this case. So I selected the data, so I trained the model. You can double check yourself that I'm not cheating. And then I'm going to make a prediction for the last one. So again, so we have split our data in the train and the test. So I forgot what cut, I put the cutoff point somewhere in at the end. And then I have that, that this particular time series the model has never seen. So let's see how this prediction looks like. It is interesting. I was not sure what would come out, but at the beginning it follows it closely, then it deviates from that. I expect there's some can be explained by the weather, but what's interesting is later on it's just it matches completely. So it did find these patterns, it learned these patterns from the other time series, where it basically said, oh, typically if it's like this day of the month and this hour, then you will have peak demand, etc. And although this time series was on a different scale, I also want to emphasize for these days, the model has not seen any of the data, and also not of the other zones, right? It's not like that we decompose these zones into this one. No, this is completely new, and I think this is still a solid result. Obviously, you don't have to do this, but if you really want to make fast predictions, this is something to think about, because the prediction step, this is like literally like milliseconds. The training takes maybe a minute, but yeah. So this is my last point, and that